While this isn't a computer science class or a class in algorithm design, there will be some times when we talk about algorithms. And since this is a course intended mostly for computer science students, when it's relevant to the math we're discussing, we will take time to talk about how those algorithms could be implemented. And to do this, we're going to adopt the approach used by computer science classes where we don't expect that students will be familiar with our favorite programming language. Instead, what we're going to do is we're going to describe processes in a generic way using something called pseudocode. So I've got a simple example of a pseudocode program here, one that adds up all the even numbers between 1 and 100 that illustrates some of the key concepts, right? The first two lines here define first a variable to hold the sum and a variable I that we'll use as a counter to walk through the numbers from 1 to 100. And this symbol here, right, the dollar sign followed by an equal sign, that's what we'll use to assign a value to a variable. Right, so that's saying the value of the sum variable is 0 and the value of the I variable is 1. Right, now once we've got those variables set up, the while loop here will run the code over and over again as long as this end criterion is met. So in this case, it's going to continue to execute the code over and over again as long as the value of our counter variable is less than or equal to 100. So each time through the loop, the code checks to see if the number is even by looking at the remainder. That's what the mod function returns, right? In this case, the remainder when the counter variable is divided by 2. And if the remainder is 0, then 2 went into the counter evenly, so the counter must have been even. And in that case, it executes this line here that, again, we're using that colon equal sign, right, that assigns to the sum variable the value of the current value of the variable plus 1. Right, then finally here, the counter gets increased by 1. Then we hit the end of this block. So we jump back up to the beginning. We check that test criterion. Is I still less than or equal to 100? If it is, well, we go and do it again. And if it isn't, we fall out, right? We fall out of that loop and we just print the result. Now, there is no universally accepted way to write pseudocode. For example, I like to enclose blocks of code like the while loop in these curly braces and the code here that's part of that if statement. It's what I'm used to as a software developer. But you'll see other examples of this where the writers would leave out the brackets, right? They would take these out. Clean up a little bit. They would take these out entirely and just leave it up to the indenting, right? Everything that's indented one step from that if block, from that if line, is what's executed if the condition is true. And everything that's indented one level from the while statement is part of the while loop. Okay, so I want to look at another example of this, and I want to talk about, to do this, I'm going to use as an example the process of taking a decimal number and converting it to a binary number. Now, in the previous lectures, we talked about doing this by writing 412 as the sum of numbers that are powers of 2. Right, the smallest power of 2 less than 412, that's 256. So I would write 412 equals 256 plus, and just kind of working my way down there. And that works, but I don't think it's the easiest way to do it. It's the way that I think is most commonly taught. And it does make a lot of sense if you're thinking of binary numbers versus decimal numbers, but I do think there is an easier way to do this, and it's definitely a way that I think is easier to write code for. And so let's talk about how we do this, right? What I'm going to do is I'm going to take 412 and I'm going to repeatedly divide it by 2 and look at the remainders, right? So if I do 412 divided by 2, that is 206 with a remainder of 0. Now I'm going to do it again. I'm going to take 206 and divide that by 2, and we get 103 with a remainder of 0. And I'm going to keep doing this, right, over and over and over again. Right, so I'm going to write some of these out, not talk about them quite as much. 103 divided by 2 is 51, remainder 1. 51 divided by 2 is 25, remainder 1. 25 divided by 2, that's 12, remainder 1. 12 divided by 2 is 6, remainder 0. 6 divided by 2 is 3, remainder 0. 3 divided by 2 is 1, remainder 1, and then we get to the end. 1 divided by 2 is 0, remainder 1. And that's how you know you got to the end, when you get to 0. Right? When you do the division and you have 0 remainder something, that's how you know you're finished. Okay, so what is the answer to my question? How do I take this information and get the binary value? Well, all you have to do is read the remainders backwards. Okay, so I'm going to start down here and read the remainders back up to the top. And if I do that, I get 1100, 1110, base 2. And there you go. Right, that is the binary version of this decimal number. So I want to write pseudocode for this. That's what we're going to do on the next slide. But before I do that, I want to kind of take a step back and think about this procedurally. Right? You notice how there's a loop here, like we saw in the previous example. You're doing this operation, this division by 2, repetitively. You're doing it with a different number every time, and you're keeping track of the results, and you have an end condition, right? You know to stop when you get to 0. Okay, so how can we implement this? Using pseudocode. Well, I've got an example here, right, of how I would do this, and it does illustrate a couple of concepts or a couple of new things. When we're writing pseudocode, first, we don't rely any more than we really have to on outside functions, okay? Because sometimes, and I'll talk more about this when we get to the end here, there are functions that are language specific. So if we do use a function, we need to think about 2 things. First, we need to make sure that it's generic. That's the kind of function that every programming language is going to have. And second, this isn't so much a consideration for this class, but later on, many of you'll probably take an algorithms class. And you want to make sure that you're using a function that doesn't somehow, even by just a little bit, slow the code down. Right? Because in an algorithms class, you're going to be really focused on determining how efficient algorithms are. So anything that has the potential to slow the code down is going to be a concern. Okay, so let's take a look at how I did this. First, I initialized the decimal variable here, and that's the number that we've actually been asked to convert to binary. Then I initialized this output function. That output function, this output variable. That variable is what's going to end up holding our final result when we get to the end of this. And what I want you to notice here is this output, I didn't initialize it as a number. Okay, I've initialized it within these 2 double quotes. It's what's called an empty string. In other words, it's a text value, not a number. All right, that's going to be important down the line in a minute here. All right, so now here's my loop, right? As long as that decimal, the value of the decimal variable is greater than 0, do this over and over again. I want you to think for a second about what that means. Yes, the value of decimal is going to change as the program goes along. So it will not be 412 still when we get to the end. That may or may not be important to you, right? Depends on what you're actually doing with the broader program that this is a part. But just keep in mind, we are going to be changing that value. All right, so now look at what I do here, right? Remember, I'm using this mod function again. That mod function, remember, returns the remainder when, in this case, the value of decimal is divided by 2. So it's going to be either a 0 or a 1. And what do? Well, I add that onto the beginning of the output variable, right? Then on my so you see there, that's the step where I'm really building up my final result. Then here on the next step, this is the step where we define a new value for decimal, right? I take the old decimal value and I divide it by 2. Remember, this is what we did in our algorithm, right? And then I use this floor function, right? What a floor function does is it takes the number and it rounds it down. So 3.1 becomes 3, 3.5 becomes 3, 3.7 becomes 3, right? It basically just strips the decimal part off, right? That becomes the next number that we're going to test, right? And eventually, we know, we saw in the last example, eventually that decimal value is going to become 0. When it does, this test criterion is no longer going to be true. We're going to be finished. We're going to drop out of that loop and output the result. All right, so there's our pseudocode, right? Our pseudocode representation of this algorithm for converting a decimal number into a binary number. Now, one last thing I want to point out about this pseudocode is obviously there's no programming language that exactly matches everything I've done here. This code is absolutely not executable, right? If you wanted to actually implement this, then you would have to think about the specifics of the language that you're using, and you know, does your language use brackets? Do you use these curly brackets? Does it put the stuff after? Does it put the criterion for a while in parentheses or not? Does it use this symbol here for assignment or just a regular equal sign? Down here, this line, for example, where I add the new number onto the output variable, right, where I'm building up this string, never in a million years would I do that in Java, for example. Java has specific functions that you need to use for memory management purposes, technical Java stuff. But if you're manipulating strings in Java, you really need to be sure you're using those functions, right? Rather than just this literal gluing it onto the front like I did here. So I absolutely encourage you, especially if you're a computer science student, start picking up a programming language if you haven't already. It's going to be a very important tool. And I think you'll find that in computer science classes, it's not something they spend a lot of time on. There's often an assumption that you already know at least one programming language and can implement, you know, simple algorithms like this in it. So another thing for you to practice on. Okay, so this wraps up the end of our discussion of integers and the way the integers can be represented, some of the things we can do with those representations. In the next lecture, we're going to kind of take the next step, and we're going to talk about divisibility, right? What it means for one number to be divisible by another. And again, in that lecture, we're going to be building up to looking at a specific algorithm. We're going to be looking for an efficient way of finding the greatest common divisor of two numbers.